Welcome, everyone. Thanks for joining us today for our webinar, Learning from Past Incidents, the LG Polymers Vizag gas leak. My name is Colin Armstrong from Accutech, and I'll be moderating today's webinar. Some of you may remember me from the last webinar we hosted in this series where I presented on the topic of facility siting. I'm here now to help moderate today's webinar for our presenters. First, some information on the meeting platform. The navigation bar on the left side of your browser window on your screen includes a button to make the presentation full screen. You can also switch the audio to a phone connection as well. And there's a Q&A button there where you can submit any questions. I'll be collecting those questions for discussion at the end of the presentation. First, a little bit about us here at Accutech. Accutech was founded in 1994. We are a global leader in process safety and security, providing management, technical consulting services, world-class training, and enterprise risk management software. Our core services are enterprise process safety development, auditing and benchmarking, process hazard analysis, facility siting, QRA, investigations, as well as security services, security risk assessment, waterway suitability assessments, and emergency and crisis management consulting and planning. Today's session will be led by Accutech process safety experts Vijay Mandlik and Marty Rose. Mr. Mandlik is a senior consultant with Accutech based in India. He has over 30 years experience in operations, development, and safety roles in India and Norway. He's worked in petrochem, offshore, explosives, and other chemical manufacturing facilities, and he brings expertise in PHA, PSM implementation, training, and auditing. Mr. Rose is a manager of Accutech's Eastern Business Unit out of Philadelphia, Pennsylvania. He's experienced in process safety, security, engineering, and operations. He's a leader in process safety auditing, PHA, LOPA, and inherently safer technology reviews. He has published numerous technical papers on process safety and contributed to multiple CCPS guidelines and books. And now I'll turn it over to our presenters, Marty and Vijay.
Thanks, Colin. This webinar is based on the report of a 5-member high-power committee, which was constituted by Government of Andhra Pradesh under the chairmanship of Mr. Niraba Kumar Prasad, IAS. He is the Special Chief Secretary to Government. The terms of reference for the committee were to inquire the reasons for the leakage, verifying whether the company had adhered to all the safety protocols, study long-term effects of gas leakage on the surrounding villagers, if any, recommend proposed action to be taken against the unit if they are found defaulters, suggest measures to be taken by the industrial units, similar handling of the materials there to prevent such mishaps. This committee had visited the site twice. They carried out inspections at the site, discussions with all the stakeholders, reviewed technical documents, consulted other technical experts in the field, and prepared a comprehensive report and submitted it to the government on 17th of June 2020. There's some brief history about the site. This site has gone through multiple hands of the companies. Initially in 1961, alcohol manufacturing was started from molasses by Sri Rama Mills, which was taken over in 1962 by Hindustan Polymers. And Hindustan Polymers started their manufacturing of polystyrene and copolymer in 1967. Further, in 1973, the company started manufacturing of styrene monomer. Later on, in 1978, HPL merged with McDowell, which terminated styrene manufacturing in 1993. And then later on, LG Chemicals acquired HPL in 1997 and renamed the company as LG Polymers. Currently, the LG Polymers had spread about over an area of 213 acres, and it was engaged in manufacturing of polystyrene and expandable polystyrene and handling hazardous materials like styrene, ethyl benzene, pentane, etc. LG Polymers also expanded the manufacturing capacities from time to time. These are basic properties of styrene, which is a highly flammable material, which has a flash point about 31 degrees centigrade. Most of the time, temperature in that part of the world remains closer to that or higher than this. It is also toxic with exposure limits of 50 ppm for TLB and the short-term exposure limit of 100 ppm and immediate dangerous to life and health concentration of 700. This is a highly reactive material and it can polymerize with an exothermic reaction. The rate of polymerization also increases with the increasing temperature, but this can be certainly controlled if the inhibitor's concentration is maintained at the required level. What happened on that fateful night of 7th May 2020 was that LG Polymers was in process of restarting the plant after the lockdown when this event had happened. Uncontrolled styrene vapors were released from the breather valve flame arrestor deep hatch of one of the M6 storage tanks. There were two storage tanks, M6 and M5, and from this tank there was uncontrolled release of styrene vapors. Maximum temperature of this tank was noticed at around 154 degrees centigrade, which is equivalent to 1.25 atmospheric pressure, and this led to uncontrolled release of styrene vapors and affecting nearby villages. There were about 12 fatalities, 585 people were hospitalized, and loss of livestock and damage to the environment. This probably caused because of the polymerization and runaway reaction of styrene due to increased temperature. And this webinar is discussing about the reasons why it would happen. This is the brief chronology of the events that occurred on that night. The plant was being restarted after a lockdown period due to COVID-19 pandemic situation. The plant was down from 29th March till 6th May. There was very less manpower at the site than the usual deployment. Startup activities were initiated on 6th May, and on early hours of 7th May, the tank temperature started increasing. Around 2:54 am, gas detector alarm was heard in the DCS. The DCS operator informed the site personnel around 3:02 am, and after that, between 3:30 to 3:35, the director of safety heads, police, fire service, etc. arrived at the site, and the evacuation of the site personnel was started. Simultaneously, the tank police also started using the deluge system. Around 5:15 am, they started dosing of high temperature inhibitors, NDM and TDM. At 6:30 am, the styrene pump out from the storage tank was started to reduce the inventory in the storage tank, and the inhibitor addition was stopped. It was continued till 3 p.m., but the tank cooling was still continued as the temperature was still on high side. Around 9:15 p.m., additional evacuation of residents on the upstream side of the plant was started because people were getting affected because uncontrolled release of styrene. The maximum temperature was observed about 154 degrees centigrade around 10:45 p.m. and still the tank cooling was continuing. What went wrong here? As the father of process safety, Trevor Klitz, had said, a case history shows that an accident generally does not have one cause, but it has many, and that the deeper we go, the more causes we find. Every incident takes place when there are multiple failures. Human failures in design, operation, emergency response were evident in this incident as well. Similar failures were observed in Bhopal gas tragedy, which took place in 1984. This emphasizes the importance of implementation of process safety management systems consistently in everything associated with a chemical processing facility. If hazard identification, risk analysis, operational discipline is of high standards, then certainly such incidents can be prevented. Here, there are some contributing factors which the report has identified. It can be seen here. There were failures with respect to the tank design, tank temperature measurement and control, recirculation and refrigeration system, inhibitor addition protocols, and the polymerization runaway reaction which caused because of thermal or catalyzed polymerization. This conforms to the famous Swiss cheese model, according to which several failures in the protection layers, when they get aligned, and the incident happens of this magnitude. Now I request Marty to take over with respect to some features about the tank design. Yes, Marty, please.
Okay, thank you, Vijay. Okay, let's talk about the M6 tank design. The M6 styrene monitor storage tank is a vertical atmospheric tank with a capacity of about 800,000 gallons of unlined mild steel. It's equipped with a set of pumps that can circulate the contents through an external refrigeration unit. The cooling system is operated manually based on tank temperature. However, during the plant shutdown, it was operated daily only during daytime working hours. The tank is insulated to prevent external heat gain, which would increase the cooling demand. It was built in 1967 for molasses storage, when the plant was used to produce alcohol from molasses, and was repurposed for styrene storage in 1977, when the plant began producing styrene monomer. It's equipped with a flame arrestor vent, a dip hatch vent, and in addition, there is a foam injection connection on top of the tank. In the background, you can see the adjacent M5 tank, which is also used to store styrene monomer and has a similar setup. The M5 tank is a new tank and was installed in late 2019. There were several issues with the design of the M6 tank. One problem with the tank design is that it has an internal roof support structure which provides additional surface area for styrene vapor to polymerize and accumulate, which forms stalactites inside the tank. Also, originally, the styrene circulated back to the tank through a float valve, which floated on top of the liquid to provide circulation and mixing from the bottom of the tank to the top. However, in 2019, this float valve became stuck in the stalactites that had formed on the top of the tank. And the site decided to change this setup from the float valve to a fixed dip pipe to the bottom of the tank, which resulted in the loss of mixing from bottom to top. Liquid was now withdrawn from and returned to the bottom of the tank, which, as we'll see, created layering and temperature control issues. This was increased due to the lack of fresh styrene unloading during the COVID-19 lockdown in the past several months. By comparison, the M5 tank has an external roof support structure which avoids the stalactite formation issue associated with the internal structure. In addition, there has never been a mechanical integrity inspection of the tank in the 53 years that it's been in operation, including the 43 years in styrene service. This includes an evaluation of the fitness for service of the tank and a life extension if warranted. As indicated, the material construction is unlined mild steel, which serves as a catalyst for styrene polymerization. Lined steel is recommended to prevent this potential from occurring. Another issue is that the tank is vented directly to atmosphere instead of to a mitigation system for routine and emergency venting, such as a flare or cryogenic condensing system to prevent release to the atmosphere. One additional problem was that the plant noted that there was a large crack on top of the tank at the foam injector connection that had existed for some time. And again, the recirculation loop design change created an issue with loss of mixing, which you'll see in the next slide. Here you can see the circulation loop modification. On the left, styrene is withdrawn through the red line to the refrigeration system and returned to the tank via the blue line and a float. The modification eliminated the float and a dip leg design was installed in its place. This represents a change that was not adequately evaluated through a management of change program in order to determine what impact the change might have on safety or operations. There were also issues associated with maintenance of the M6 tank. From vendor literature, we see that cleaning of the tank at least every 2 years to remove accumulated polymer is recommended, in addition to having the internal lining or coating to minimize polymer formation. However, the plant policy was to clean the tank every 5 years, with the most recent cleaning being completed in 2015. This allowed for a significant accumulation of polystyrene polymer inside the tank. In addition, an inhibitor, TBC, is used to inhibit styrene polymerization during normal operation at low temperatures. Now, this is added to by the manufacturer to the styrene received at the plant by tanker truck. Although the plant should have been able to add TBC to the tank if needed, however, they did not have any stock of TBC at the time of the incident. However, the presence of various contaminants in the tank, such as rust from the unlined interior surface, can also catalyze polymerization, which can exceed the ability of the TBC to mitigate. And now we'll turn it over to Vijay to talk about temperature measurement and control.
Apart from the tank design and the issues with respect to the maintenance of the tank, there were some issues with respect to the temperature measurement and control system. The temperature measurement was restricted only to the bottom zone of the liquid, whereas the top and middle zones may have different temperatures because of poor mixing. As we saw, the modification was done without ensuring that the mixing would be adequate. There should have been at least 4 to 5 temperature measurements along the 12-meter height of this tank to measure the true temperature of the different zones in the tank. The tank M5 had temperature measurement probes at 3 locations, but M6 had only at the bottom. And the operations staff always believed that the bottom temperature to be the temperature of the whole bulk of the liquid, which was incorrect, and that led to the thermal stratification. As can be seen in those figures, the first figure indicates that the bottom temperature, even though it might indicate 17 degrees centigrade, the top layer could be at around 35 degrees centigrade, wherein the polymerization can initiate. This also causes issues with respect to the TBC content. If the temperature is around 17 degrees centigrade, the TBC content, which is expected to be maintained at 15 ppm, would remain uniformly throughout the storage tank. But if there is a higher temperature on the top layer, then certainly TBC inhibitor content would also reduce periodically. This poor mixing due to the modification, inappropriate temperature measurement, and lack of auto temperature control system must have led to the thermal stratification in the tank. This graph shows the temperature profile of the M6 tank. It is evident from this temperature graph that the temperature was by and large stable below 20 degrees centigrade until about 3 a.m. of 7th May. And then it started increasing thereafter. The rise in the temperature was sudden and occurred at fast rate, thereby pressurizing the tank. The rate of increasing of the temperature slightly reduced between 5 a.m. to 9 a.m. and thereafter again started increasing, even though the tank cooling up measures were being undertaken by the site using the dilute system. From 3 p.m., there was a further increase in the rate, and finally the temperature peaked around 154 degrees centigrade. That was recorded around 10 p.m., which was equivalent to 1.25 atmosphere pressure, and that continued the release of styrene vapors in the uncontrolled branch. Apart from the cooling system, there were The cooling methodology, there were issues with respect to the recirculation refrigerant system. The preferred storage temperature is in the range of around 10 to 18 degrees centigrade with upper limit of 25 degrees centigrade. If the temperature approaches 20 degrees centigrade, the tank contents must be cooled. It was revealed that there was no high temperature alarm on the tank. There was a practice to operate the refrigerant system manually during 8 a.m. to 5 p.m. every day. However, on 6th May, the system was stopped at around 3:45 p.m., assuming that the tank is cold enough. Temperature of liquid styrene monomer is very crucial factor. The temperature maintenance throughout the large storage tank at around 15 to 20 degrees centigrade is essential in the light of possible runaway polymerization. For a place like Visakhapatnam, the temperatures mostly ranges from 20 to 36 degrees centigrade. It is essential to operate the refrigerant system on a continuous basis to ensure that the temperature at all levels is below 20 degrees centigrade. It was also put forward possibly the styrene contamination could have happened due to the leaks in the refrigerant system because the mechanical integrity of the cooler into the refrigerant system probably was not ensured. Possibly there were chokings inside the refrigerant system walls and lines which might have clogged during the shutdown period, and the contents could not have been cooled as the pump motor had tripped due to the viscous polymer present. Now we'll talk about the testing protocols. Marty to take over.
Okay, as mentioned earlier, TBC is used to inhibit polymerization of styrene at low temperatures. For the temperature range normally maintained in the tank, this requires a concentration of 15 parts per million of TBC to be maintained, as Vijay indicated. Routine sampling and analysis should be done to confirm the proper TBC level, ideally daily sampling from both the top and bottom of the tank. During the lockdown, however, samples were taken sporadically from the bottom and top of the tank. Due to the change in the circulation system and loss of mixing, samples taken were not representative of the bulk contents of the tank. It should be noted that the plant had not added TBC to the tank in at least 10 years. Due to the high turnover of material in the tank and the addition of TBC by the vendor to the deliveries, there wasn't a concern about the TBC depletion under normal operating conditions. However, there were no styrene deliveries or usage during the lockdown period, which allowed the TBC level in the tank to drop, again undetected and aggravated by the loss of mixing due to the aforementioned circulation piping change, which also allowed for temperature differentials inside the tank. Higher temperatures increase the depletion rate of the inhibitor. Another issue with styrene is that when it is exposed to heat, it forms free radicals. These styrene radicals react either with oxygen to form peroxide radicals or with styrene to form the polymer chains. In the presence of sufficient oxygen, the peroxide formation is significant because this reaction of peroxide radical formation is much faster compared to the polymer formation with styrene. So oxygen works as a polymerization inhibitor, while TBC controls its efficient use. So a certain level of dissolved oxygen is desired to inhibit polymerization. You can see from this chart that the level of dissolved oxygen significantly affects the active life of the TBC inhibitor. At least 8 parts per million of oxygen is a key parameter in order to inhibit the styrene free radical polymerization and make the TBC functional. Unfortunately, there was no monitoring device or monitoring system in place to measure the level of dissolved oxygen in the styrene monomer tank, in the M6 tank, or in any of the other styrene tanks at the facility. This is not acceptable as dissolved oxygen is a critical input to the effectiveness of the inhibitor. As previously mentioned, polymerization generally takes place by free radical reactions, which are initiated by high temperature or a catalyst such as iron. The polymerization rate increases at higher temperatures, which is increased due to the heat generated by the exothermic polymerization reaction. Since there's evidence that effectiveness and concentration of the TBC inhibitor was reduced and bulk mixing and cooling was inhibited, it's apparent that this incident was caused by a runaway polymerization. Lack of dissolved oxygen may also have been a contributing factor, as well as the presence of polystyrene stalactites, which may also catalyze further polymerization if they contact the liquid. Analysis records indicate that the level of polystyrene contamination of the tank increased slightly in the month prior to the incident and dramatically in the 10 days prior to the incident. However, no action was taken by the site as this was considered to be a quality issue and not a safety issue. The increased temperature due to the runaway polymerization caused boiling of the styrene and subsequent vapor release from the vents as well as from the large crack at the foam injection point. Had these not vented the vapor, catastrophic of the failure of the tank could have resulted. Now this chart shows the increase in polymer formation over time, including the modest increase in the month prior to the incident, as well as the significant increase in the 2 weeks prior to the incident, which was a warning sign that should have triggered a response, but did not. Next, BJ will talk about consequences of the incident.
So these were the major contributing factors which caused this incident. There was about 1,842 metric tons of styrene present in the tank on the day of the incident, and it is estimated that about 818 metric tons styrene vapors were released, and that caused the styrene concentration above 1100 ppm, which extended up to 420 meters from the storage tank. This resulted in 12 fatalities and hospitalization of 585 people from nearby villages. And this required evacuation of more than 20,000 people from the nearby areas. Around 17,000 houses and residences were evacuated. This figure here indicates the area of influence of the chemical vapor or gas classified by the Aloha model. There are 3 zones indicated here: red zone, orange zone, and yellow zones. The predicted threat zones for this case, with different wind directions of 120 degree, 145 degree, and 172 degree, have been shown here. The prevailing wind direction resulted in the spread of the styrene monomer vapor cloud towards the villages in that particular direction. The zones indicated in the picture are defined as the areas that may cause environmental impacts in the vicinity based on the styrene concentration limits of 1100 ppm, 130 ppm, 20 ppm, based on the AEGL values here. Marty would talk about the root causes here.
Okay. The investigation report lists 13 root causes of the incident. These include modification of the tank recirculation piping, as we've mentioned, inadequate operation of the refrigeration system, inadequate temperature measurement and lack of alarms, lack of a tank lining and the external roofs and external roof supports, as well as internal cleaning, as recommended by the supplier. Also, the lack of TBC and dissolved oxygen monitoring, lack of procedures for maintaining the styrene inventory during the COVID-19 lockdown, which stopped receipts and transfer of styrene from the tank. Under normal conditions, there was sufficient tank turnover to minimize polymerization due to mixing and TBC level. No special provisions were made for maintaining the tank contents during the lockdown period. Another key cause was that there was no comprehensive process safety management system at the site, including process hazard analysis, risk assessment studies, incident investigation, and other elements. There was a significant lack of knowledge of the properties and hazards associated with styrene. There was a lack of competency in handling styrene due to the retirement and loss of experienced technical personnel. And then also there was a lack of knowledge and talent among top, middle, and shift management in LG Polymers. Most of the shift supervisors and engineers were not qualified or experienced, and therefore their knowledge and skills were not adequate when faced with a challenge or an emergency such as this. As discussed previously, the fault tree for this incident identifies many root causes and contributing factors, including the poor tank design, including the internal roof structure, lack of lining, lack of temperature monitoring, circulation modification, and lack of cleaning. The lack of qualified and competent technical personnel. Poor temperature monitoring and control, including insufficient chiller capacity, lack of mixing, lack of temperature monitoring, and the heat gain due to circulation pump deadheading and inadequate insulation. High polymer content in the styrene, which was not identified as a safety issue. Lack of process safety management system, and poor monitoring and control of the TBC inhibitor concentration, including dissolved oxygen, lack of mixing, which was aggravated by the lack of turnover due to the COVID-19 shutdown. All these issues are discussed thoroughly in the investigation report. Now Vijay will cover the recommendations from the report.
Due to all these failures which were observed by the high-powered committee, suggestions to avoid the recurrence of such incident either at the site or at other sites. The tank must have a floating valve circulation technology which provides adequate styrene circulation and mixing to have a uniform mixing and temperature control throughout the tank. There must be provisions for mixing in case of this circulation system fails. The material of construction of the tank should be carbon steel with coating inside. The tank cleaning and coating should be carried out with outside structure. All styrene monomer tanks should have flare system or cryogenic system so that there is no styrene vapor release even under normal circumstances. Air pollution. Be multiple continuous temperature measurement probes at different levels of the tank and linked to the control room with an alarm. Few more suggestions were there with respect to automatic monitoring of inhibitor content and dissolved oxygen, ensuring the siren during emergencies for raising an alarm to nearby community in case of any release. Units or factories storing or processing styrene monomer must undertake annual safety audits. SCBAs and other emergency equipment required for handling such chemical disasters should be made compulsory. Gas detectors shall be provided at the boundary of the factories with an alarm in DCS. Process safety management shall be made mandatory for all the factories covered under MS-ISC rule. And the hazard identification studies like HAZOP and the resolution of recommendations shall be made compulsory for all hazardous process factories or units where there is a processing or storage of hazardous chemicals takes place. There was a National Green Tribunal was also established. This tribunal also gave some suggestions. There are really high-level suggestions with respect to ensuring compliance with the chemical accident rules related to emergency planning, preparedness, and response, compliance to Factories Act of 1948, compliance to requirements of Petroleum and Explosive Safety Organization, compliance to MSIHC rules of 1989. And apart from that, to ensure the emergency preparedness by conducting periodic mock drills, observing and imparting training to the emergency personnel available at site and off-site.
Well, thank you, Vijay, and thank you, Marty, for the presentation. It's a good review, and I think it illustrates how, as you noted at the beginning of the presentation, Vijay, it's not just a single major failure that occurred, but a series of small failures that aligned. And we have to remember that those small failures can seem inconsequential on their own, but we have to remain vigilant in process safety, because if they're allowed to exist and they do eventually align, we do end up with catastrophic incidents. I thought it was also quite interesting that this was so deeply related to operational changes that had happened at the facility related to the COVID-19 lockdown, that the facility had been shut down, and this was during a restart. Startup's always a difficult time, and I think the challenges that operating companies are facing right now with COVID make those operational changes even more difficult than ever. But thank you both for all of that information. We've collected some questions throughout the presentation. If anybody has any additional questions, you can submit those, and we can go through them in a moment here as I pull them together. Just a side note as well, we do have 3 more webinars still upcoming in this webinar series. The next one is on how to improve PHAs, and that'll be presented on August 25th. And then we have one about inherently safer design, and another case study on a previous incident, and that is about inadvertent mixing. But moving over here, Vijay and Marty, to the questions that have come in. A first one, a plant like this, how are they supposed to know that a potential for a catastrophic incident like this could occur? What do you think they were really missing there?
Yeah, I would take it. Basically, the hazard screening for the hazardous materials which are being handled at site must be carried out. The properties of like flammability, toxicity, reactivity, etc. must be thoroughly understood. The analysis like qualitative and quantitative risk assessment shall be performed so that the consequences are fully understood and the adequate measures have been implemented at the site with respect to design, operations, technical or non-technical measures, the emergency preparedness, training with respect to that. So that can certainly prevent such catastrophic incidents.
All right, thank you, Vijay. Here's a good one. This relates back to an inherently safer design, which is a topic we have upcoming. But were there any inherently safer design recommendations made, or that you all see here, do you think should be addressed?
Yeah, basically the hazard identification, if it is done at the early stages of the project, and also when the modifications are being carried out, then certainly such issues can be avoided. And with respect to ISD, the system should ensure that there are adequate control measures in place to avoid the thermal catalytic polymerization of this magnitude which happened.
I don't recall any recommendations specifically in the report related to inherently safer design.
Right.
Because this is a material that is unstable. It has an inhibitor. Again, that's a control, an active control. Under normal circumstances, the inhibitor comes in with the monomer, which should not present a concern, and that has been the case largely. But in this case, there were other factors, obviously, that came into play that caused the inhibitor to not be adequate.
Thank you, Marty. And there's a couple questions here related to safety culture or safety competency. what could the site have done to improve that safety culture or safety competency at the facility? What opportunities do you see there?
Yeah, well, I take it. See, basically, identification of competency areas, criteria, the competency mapping, for which position, what competencies are required, whether it's design, the qualification, or the experience. So that has to be mapped. Conducting the gap assessment with respect to the competencies required and identifying the training needs, imparting the training, evaluation of those training, and certification, formal certification that the person is fit enough for conducting these kind of assignments related to process safety. Evaluate and confirming the required competencies have been achieved for each position. That will certainly ensure that the people are trained well enough to avoid such kind of incidents. With respect to culture, yes, it has to be demonstrated at all levels, at all times, consistently.
And if I can add to
Marty,
that,
you would like to add anything?
yeah, if I can add to that, so the fact that they had turnover of experienced people was one of the contributing causes, and the people that were at the plant were not experienced or knowledgeable in styrene. There should be a way to retain institutional knowledge, and this is a industry-wide issue. When people with 30, 40 years of experience leave, they take all that knowledge with them. And so, companies should try to find a way to capture that institutional knowledge in a written form and make sure it gets transferred to the people that remain at the site, so that you don't have that massive loss of institutional knowledge. And apparently that did not occur in this case. The people who were operating the site lacked the knowledge and awareness of many of the hazards of styrene monomer. I mean, the fact that the concentration was increasing of polystyrene in the tank, seen as a quality issue versus a safety issue, I mean, that was a clear warning sign. And that's something that should be well known, from the literature, from experience, and the properties of styrene. And as far as culture goes, I mean, that comes largely from the top. And clearly there were issues with the culture. We can point to the large crack on the top of the M6 tank that had been in place, which in this case helped mitigate an overpressure situation in the tank. The vent may or may not have been adequate, the other two vents. So this provided another way to relieve pressure. But, this is not the way to operate a tank. And clearly mechanical integrity was lacking here and accepting a deficiency that really should have been corrected previously.
Yeah, good observation there, Marty. A question here, I think, Vijay, this would be a good one for you to address. There's a question: is PSM mandatory in India for chemical industries? What's the status of PSM regulations in India?
Okay, as of now, the regulations are not there. Clearly, PSM implementation regulations do not exist. But certainly there are other regulations which we talked about with respect to MSISC rule, the Factories Act, the Emergency Preparedness Act. So there are several different rules or acts which stipulate the requirements essentially for all the 20 elements risk-based process safety management to get adhered to. So it is certainly the voluntary exercise. As of now, PSM auditing is not mandatory regulatory like what is done in US, but certainly it's a voluntary exercise to ensure that all the 20 elements are implemented consistently throughout the factory.
And it sounds like is there discussion that an incident like this may be changing that in the future, or has that not come about?
Yeah, it could certainly come again because even the high powered committee has also mentioned that PSM should be implemented. It's not, as of now, it is not regulatory, but the committee has mentioned that PSM implementation should be made mandatory. So certainly sooner or later these regulations would come in here.
If I can add to that, it's also imperative on the corporate parent. In this case, LG Chem, which is based in Korea, is a multinational company with multiple plants, and a progressive company should establish company-wide standards for things like process safety management and apply them to their sites worldwide, regardless of whether there are regulations or not. I formerly worked for a major chemical company that did this because, obviously they don't want an incident like this to happen anywhere, regardless of what the regulations require. At a minimum, company standards would have to be met, and then government standards, if there were any, in addition to that. So I think in this case, there were some things that were missing from just a corporate governance standpoint that allowed this incident to occur.
Yeah.
Okay, I'm just taking a look here. There's still a few more questions rolling in. One question here, what caused the 12 fatalities? Those were all off-site, that's correct?
Yeah.
On-site fatalities, and those were exposure to styrene vapor, right?
Yes. And the concentration were certainly much more than the 1100 ppm was estimated at the boundary limit of the factory, and nearby around 420 meters area was affected due to high concentration, and styrene being toxic, the people succumbed to those injuries.
Yeah, and it's this release occurred, in the nighttime. Do you know what the climate was like at that time, Vijay?
Yeah, probably the
condition.
the night. Yeah, the wind direction probably it was towards 120 degree and 172 degree, as it was mentioned in that Aloha model also. And the villagers in that direction got affected.
Right. And likely, in a low wind speed condition, you can see in some of the photos here, it looks like a very, relatively stable atmosphere. We see some, fog sitting down near the ground from the vapor, and those very low wind speed, very stable conditions can result in very high concentrations remaining in an area for an extended period of time. And those conditions tend to occur at nighttime. But when we look at facility siting and dispersion modeling, that's a major factor in the distances and the exposure levels is the wind speed and the stability. So
that's
another element that contributed, I think, to the severity here. If this event had happened on a very windy day, the outcome could have been extremely different.
Absolutely. Yeah.
Another question coming back to culture here, and this seems to be a recurring element in the discussion. What are the key elements for a world-class safety culture? I think that's a good question, because culture is a hard nut to crack.
Well, if I could jump in here, so culture, is a collective system of beliefs and behaviors at a site where everyone agrees that things should be done in a certain way, and a positive culture promotes the positive behaviors that lean towards safety and process safety and environmental protection, and a poor safety culture does not. In this case, something as simple as open vents to the atmosphere. Not just for emergency situations, but for normal operations. There's breathing that goes on. Whenever you fill the tank, you're going to vent, and so there's going to be a kind of a routine emissions from the tank. That's a cultural issue. That's saying that that has allowed to go on. So people respond to those, and what's important to the company generally is what's important to people, and as well as safety and process safety, things like inspections and shutting the plant down to correct things rather than continuing to operate with a faulty situation. those are all parts of culture that were apparently remiss in this case.
Yeah, sometimes the deviations also are accepted by some levels, and that becomes a norm sometimes, and that's how the culture either goes down or gets consistently improved. That depends on, that has to be demonstrated at all levels in the factory, whether it's a junior employee or at the company owner. So all of them need to adhere to the safety requirements at all stages. Then the culture builds up, and then certainly a world class sound process safety culture gets nurtured.
All right. Thank you all. And I think I'll close it out. We've got one last question here that I think is a good one. And then I think we'll close out the presentation here. But how do we ensure that lessons learned from incidents such as this are maintained, over future generations, and that we don't repeat history?
Well, that comes from a sharing of knowledge, basically. When an incident occurs, it has to be shared amongst the industry, especially the industry that handles a specific chemical or that has that situation, like styrene. But more broadly, sharing amongst the industry. And I know that CCPS plays a part in that, in sharing incidents, for example, through the beacon. There are many other avenues, and obviously with the internet, there's information easily shared worldwide on chemicals, on incidents that have occurred, and it really behooves each facility to understand what has happened at other sites that could happen to them. And for example, in the report, it talks about previous incidents involving styrene, and it's pretty well established that styrene, if not, managed properly, can result in this runaway polymerization. There was an incident in Ohio, in the U.S., several years ago, where a rail car sat for 9 months on a siding with styrene, unbeknownst to pretty much anyone, until it started venting styrene vapors, because it had sat. It's got a shelf life. The TBC inhibitor, was exhausted. Temperature had increased just from weather, and that was one of the incidents. And there's several that are explored in the literature related specifically to styrene. But an incident like this, similar to the Bhopal incident, is just again a textbook case of the different factors that can go wrong, that can lead to a catastrophic incident like that, and especially under abnormal circumstances like a shutdown, a COVID shutdown, combined with the loss of personnel and knowledge. So those are all important learnings, and it behooves us in the chemical industry to know what's happened when we do PHAs at our sites, to look at not only the incidents that have occurred in our facility, but also to look at incidents that have occurred elsewhere and see if there's any analogy where, okay, this could happen here. Let's prevent it and learn from others' misfortune.
Yeah, particularly India has experienced several incidents in past 6 months, maybe, and probably we can attribute that to the availability of less manpower. The well-trained manpower is probably not able to attend to the factories at all the times, and there were some restrictions with respect to inspections, maintenance because of COVID situation here, and this also caused several incidents. Okay, and there are a lot of learnings from that, and certainly people would look into that, what went wrong, like what we have done now, and the corrective measures would be undertaken at all times.
Yeah, I think it all links back to that process safety competency and process safety knowledge, right? And
Right.
The other place, then the way that we learn from these lessons, they get brought up and discussed in our risk assessments and our analyses. And there's another point where this was missed, and something that didn't happen to catch these types of hazards beforehand.
Right.
Right. Well, thank you both very much for the presentation and all of the questions. And thank you everyone in the audience for attending. And we appreciate it. And hopefully we will see you on Tuesday, the 25th for our next webinar in the series. Thank you all again.
Okay.
Bye-bye.
Okay. Thank you. Thank you, everyone. Bye-bye.